Right, ladies, today we are looking at critical angle and total internal reflection. So let's take a look at this first. So just to summarize what we've already done, we've got light traveling from water into air. So you should know that water is optically more dense compared to air, and the light ray will speed up as it travels from water into air, and it will bend or be refracted away from the normal. So you can see I've drawn in the normal. This is the incident ray. Here I've got the angle of incidence. This is my refracted ray, and over there I've got the angle of refraction. Now, if I increase the angle of incidence, what is going to happen? So yeah, same thing, light's traveling from water to air. The angle of incidence here is greater compared to there. So it is still going to be refracted away from the normal, but now the angle of refraction here will be greater compared to there. If I then go even further and I increase the angle of incidence even more, I'm going to find the following situation. So the light is traveling from water to air, and you can see that the angle of refraction is equal to 90 degrees. So the refracted ray moves along the boundary between the water and the air. As soon as this happens, we then say the angle of incidence is referred to as the critical angle. So what is the critical angle? The critical angle is the angle of incidence for which the angle of refraction is equal to 90 degrees. Very important, for there to be a critical angle, light must be traveling from an optically more dense medium to an optically less dense medium. Then over here, you've got your definition for critical angle. Critical angle is the angle of incidence in the optically denser medium, so the water in our example over here, for which the angle of refraction in the optically less dense medium, the air in our example, is 90 degrees. So what is the critical angle? It is the angle of incidence for which the angle of refraction is 90 degrees. Then, if we go even further and we increase the size of this angle even more, so the angle of incidence becomes greater than the critical angle, then the following is going to happen, and we refer to this as total internal reflection. So in our previous example, the refracted ray moved along the boundary here, but if the angle of incidence is greater than the critical angle, the refracted ray doesn't emerge, it doesn't come out into the air. It is actually reflected, it bounces back into the medium, so it goes back into water. Then we've got the incident ray, and this is referred to as the reflected ray. Once again, the normal I've drawn in. The angle between the incident ray and the normal is the angle of incidence, and the angle between the normal and the reflected ray is the angle of reflection. And as you already know, according to the law of reflection, the angle of incidence will be equal to the angle of reflection. Okay. There are two conditions for total internal reflection. Light must be traveling from an optically denser medium, which will have a higher refractive index, the water in our example, to an optically less dense medium with a lower refractive index, the air in our example. And secondly, the angle of incidence in the optically denser medium must be greater than the critical angle. Because if we go back over here, if the angle of incidence is equal to the critical angle for that specific medium, the angle of refraction is going to be 90 degrees. But if the angle of incidence is greater than the critical angle for that specific medium, what is going to happen? Total internal reflection over here is going to take place. Right, then we can use Snell's law to calculate the critical angle. And once again, I think the easiest way to explain this is by using an example. So if you look on page 117 at the worked example, they ask us to calculate the critical angle for glass. The refractive index for glass is 1,52, and this is what it would look like, because remember, it's all about light traveling from more dense into less dense. So the light ray is going from glass, refractive index 1,52, and it's traveling towards air with a refractive index of 1. So the normal is drawn in. This is going to be my incident ray. This is the angle of incidence, and they ask for the critical angle, so I know it is the angle of incidence that I'm trying to find for the angle of refraction of 90 degrees over there. Snell's law, I've just written down the formula. So refractive index is 1,52 because this is always the refractive index of the material that has the incident ray. Then sine of the critical angle. So the angle of incidence is called the critical angle because what is the angle of refraction? It's 90 degrees. And the refractive index of air is 1. So sine of the critical angle will be equal to 1 times sine 90 divided by 1,52. And the critical angle works out to 41,14 degrees. So that angle of incidence there, if it's 41,14 degrees, the angle of refraction is going to be 90 degrees. If that angle of incidence is greater than 41,14 degrees, if it's 42 degrees, what is going to happen? The light ray will then be reflected back into the medium and total internal reflection will take place. So that happens when the angle of incidence is greater than the critical angle that we've calculated here as 41,14 degrees. These formulas over here to calculate the critical angle, we can say sine of the critical angle is equal to the refractive index of air divided by the refractive index of whatever the medium is times sine 90 degrees. And we can also just say that sine of the critical angle is equal to the refractive index of air, which is always 1, divided by the refractive index of whatever the medium is. And I can do this because sine 90 degrees is equal to 1. And then lastly, some applications of total internal reflection. If I use a prism that has an angle of 90 degrees, like that angle over there is 90 degrees, so that would be 45 and that would be 45, and I've got an incident ray, and because it strikes the surface at 90 degrees, although it slows down as it enters the glass, it is not going to change direction. It strikes the surface over here, it's going more dense into less dense, but what is going to happen is total internal reflection takes place over there, and I've got an angle of incidence, I've got an angle of reflection, and again, it strikes the surface at 90, so it doesn't change direction, and it just comes straight out. Here's another example. So incident ray, over here, total internal reflection takes place. Over there, total internal reflection takes place as well. So the ray actually changes direction, and this is applied in binoculars as well as in the periscope of a submarine. So you can also just go look at figure 5.21. Right, fiber optics. Let's take a look and see what you need to know there. These are extremely thin glass tubes. They're talking about the diameter of human hair, so that is really very thin. And it looks something like this. It has an outer protective layer or outer cladding, which has a lower refractive index, and then it has the core, the inside, which has a higher refractive index. So light is traveling from higher refractive index into lower refractive index, but what actually happens over there is total internal reflection, and I've got an angle of incidence which is equal to the angle of refraction. And then Over here, same thing happens, total internal reflection, it bounces off the inside surface and again, and that is how the light travels through the optic fiber. Where is this used? It is used in communications. They say that a single optical cable can carry 100,000 telephone calls simultaneously. Fiber optics are a lot less expensive compared to copper cables, and we know with copper cables there's also the problem with theft, and if we use fiber optics that doesn't happen. And they also say that it has signals which are a lot clearer compared to when copper cables are used. And then fiber optics also used in endoscopes. These are instruments that doctors use to enter and investigate the human body, either to diagnose things, to take tissue samples for microsurgeries, and endoscopes that are used in the stomach are referred to as gastroscopes. And of course, using an endoscope is a lot less invasive compared to actual surgery. All right, guys, and that's the end of the chapter. So what you can do for me is exercise 5.5 on page 117, as well as the questions at the end of the chapter. So that's chapter 5 questions, page 120 and 121. Now this exercise is quite long. There's quite a lot of questions to answer there. So to give you a bit more time to sit and to work on those, I will post the answers for you on Thursday. Thanks, ladies.